you're watching this video, you're watching the video on misrepresenting data using graphs. In this lesson, we'll talk about what we learned about graphs and then talk about how you can use these graphs to trick people, basically. This lesson is more about understanding how graphs work, understanding how the numbers can be used to show graphs in a certain way so that it can make you believe something that isn't necessarily true. So with the title page here you can see on this graph percent who agreed with the court. We have the American parties, the Democrats, the Republicans, and independents. And if you look at this, well, the Democrats seem to really agree with the courts, while the Republicans and independents, no, they really didn't. Now, if you take a closer look and you study this graph, you'll see, oh, we start at 50 and the highest is around 62, while Republicans and independents get around 54. Well, this looks like the majority, like double the number of Democrats agreed with the court while Republicans didn't. Well, half the number did and half the number of independents did. And if we made this graph accurate, if we made this graph more representative of the data, you would see a graph more like this, right? You would see that the difference in Democrats who agreed with the court and the percentage of Republicans who agreed with the court is very small. And so you can change the parts of the graph to suit a certain narrative, to make your agenda met, right? You can say, well, the Democrats agreed with this, and depending on what you're trying to say, you could say the Democrats are real good or the Democrats are real bad, based on just this graph. When in fact, it's not really that different across the different parties. So you can change certain things about a graph to make it seem like it's saying one thing rather than another. So here we have a graph. We have another bar graph, and I'm asking the question, what is wrong with this graph based on the class? Well, we have the average score out of 100, and we have Mr. Jones's class and Mrs. Smith's class. Well, at first glance, it looks like Mrs. Smith's class is really smart and Mr. Jones's class is full of dum-dums. But look at the y-axis, this vertical axis, right? Is there a big difference between the highest point of Mrs. Smith's class and the highest point of Mr. Jones's class? Right? The most common form of changing a graph to make it misleading is by changing the y-axis. From the graph, we see that the y-axis does not start at 0. From all the graphs we talked about, all the graphs started at 0. And then we picked a number to go up by each time. Well, in this case, we started at 73, right? And we went up to 74.4. So really, we went up by 1.4%. And if you look at it, well, 73.2 versus 74%, Mrs. Smith's class is only 0.8% better than Mr. Jones. And later on in life, if you take mathematics, you'll see that statistically, in terms of probability, in terms of measurements, that's not really a measurable difference. It's not anything. It's like, oh, they may have gotten one smarter kid in that class that affected the average, right? But because the y-axis starts at 73 and the way it goes up is so small, it looks like Mrs. Smith's class is just beating Mr. Jones's class and making Mr. Jones look terrible. So changing that y-axis, changing the scale, affects how the graph looks. And so you can make one class or one thing look bigger or more representative than another. So on a proper graph, the scale should be followed all the way down to 0, right? We should start at 0 at this corner and work our way up by a certain amount. So if we were at 74, we should go up by 10s or we should go up by 5s. We shouldn't start at 73 and go up by 0.2 because these small differences look a lot bigger on a graph. So when a graph does not follow the scale or does not really start at 0, then we say that there's a break in the graph. And this should always be represented with a little symbol, like a little squiggle here, or dashed lines or sideways dashed lines on the y-axis. If you don't see this, and you don't start at 0 on the y-axis, you can say that that graph's trying to be misleading, right? So let's take a look at the graph that the way it should be represented. And as you can see, if we go up by 20s, Mr. Jones's class is pretty much equal to Mrs. Smith's class. The average score isn't that much of a difference. And so they're both doing relatively the same amount. Their classes are basically scoring roughly the same amount. But if you look at this graph, you're saying Mr. Jones sucks. But if you look at this graph, they're about the same. And that's because we started at 0 and we went up a specific amount. While here we started at 73 and went up by 0.2. So on the bar graph, affecting the y-axis, like we just saw, can make the bar graph look much bigger in one area than it should be. In reality, the grades are basically the same. But most people, the average person, is just going to look at the graph right away and go, oh, well, Mrs. Smith's class is the best. And they won't actually look at the data. They won't actually read the y-axis and see the problem with doing it this way, right? This is what the graphs should look like. This is the actual difference between the two classes, not much. But here, you can tell Miss Smith probably made this graph to make herself look good because the difference looks like it's huge when in fact it isn't. So what about line graphs? How could changing the y-axis affect a line graph? Here we see changing the y-axis here. Well, that can make the bars look bigger or smaller depending on what you want. Well, what would happen if we did that with a line graph? Well, here we have an amount of money, right? And we start at 300,000 and we go up to about 1 million. And at 2007, it's 800,000. Then we go up to just about 950,000, then drop down to 600, and a little bit less than 600,000. Right? It looks like the prize money is changing a lot or dropping a lot. But if you don't start at 0, you can make graphs in lines look more or less dramatic. Right? So here we have a graph from 0, 2, 4, 6, 8, 10, 12. We went up by 2s. And in the year 1990, we started at 2, whatever this is, whatever this graph is measuring, and we go to 1994. Right? Well, changing the y-axis so the max is smaller can make the graph look more vertical or more dramatic, right? If we go up by 1s here, right? If we go up by 1s here, we can see that, and then we lower the maximum, we can see that the line is just a little bit steeper. It looks a little bit taller. It looks like it's growing faster. While this one doesn't look like it's growing as fast. This one looks steeper. This one looks like it's going up more. And so you could say, oh, let's say we're talking about money, and this is like in the millions, from 2 million to 10 million. But if you shrink it down, it looks like it's growing so much quicker. It looks like you're getting more profit or whatever you're measuring here. So you can make something look like it's growing faster if you shrink the maximum on the y-axis. We went from 12 to 10, right? And it looks just a little bit more vertical. It looks a little bit more dramatic, right? I could shrink this down to 5 and it would look a little bit more vertical. It would look a little bit more dramatic, right? Making the max bigger can make the line look more flat. It can look less dramatic. Here we have 2, 4, 6, 8, and you can see it's growing. Whatever this is, it's growing. It's going up in numbers. Well, if you look here, it doesn't look like it's growing that much. I went up by 5s instead of going up by 2s. Sorry, not 10s, 2s. And by going up by 5s, the line looks flatter. It looks shorter. It looks more flat. And so you could say, oh, this isn't growing that fast, right? Let's say you're talking about crime in a city, and this is the amount of crime happening in a city, and this is the line you have. Well, it looks like it's growing quite fast. And you don't want to show that. You're the mayor and you don't want to show that to the people. But you don't want to lie, right? That could get you in trouble. Well, if you make the graph look bigger on the y-axis, you can say, well, crime isn't growing that fast. Crime isn't a big problem. And you can use that to change the way graphs look. You can change the y-axis, how far it goes up, to make graphs look less dramatic, to make bad news look not as bad. And you can make good news look even better by shrinking the y-axis, right? You can say, oh, but look at all the money we're making versus the crime is not going up fast. So making the y-axis bigger, right? Increasing your maximum on the y-axis, you don't need to go up to 50. The highest you get up to is 10. Why are we going up to 50? To make the line look flatter. So if you see something like that, keep an eye out for graph lines where you have a y-axis that goes up way too high, right? Going up a point or two above the highest point you get in your data, that's fine. You can go up to 14 or 16. But going up to 50 is unnecessary. It's just a tool used to make the line look flatter, right? What's wrong with this graph? What do we see when we look at this line graph? Well, we're going across time and we're going up in temperature, right? Well, 24, 25, first off, we don't start at 0, right? We don't start at 0, so it already looks like a low temperature here, and it goes up to 31, right? This looks like it jumped up like 20 degrees, when in fact it really went up by 7. And so you can make the temperature change look more dramatic by changing that y-axis, by not starting at 0, right? So the scaling of the graph also changed the graph, just like with the bars. Here, this is the graph that we just saw. And it looks like it's shooting up really fast. But if we use a more accurate representation, going up by 5s, starting at 0, always start at 0, going up by 5s, going up by a regular amount, you can see that this line is more or less flat. And the temperature sort of steadily increases, but then sort of evens out. And so you can change graphs. This is the same data. This is the same information. I just changed the y-axis. I just changed the y-axis to make the graph look different. It's the same graph. And so depending on what I wanted to sell you on, I could use this graph to say, oh, the temperatures are growing really quick. Or I could say, oh, the temperatures aren't growing that fast, are they? And so this is very applicable to daily life because this is what people, politicians, companies try to do to convince you that something's really good or something's really bad by stretching and shrinking those graphs. Here we have a pictogram, right? Which fruit was collected the most? Right? Let's say each fruit picture counts as 10, right? Well, it looks like bananas sold the most or collected the most, right? 10, 20, 30, 40 bananas. But apples are also 4, 10, 20, 30, 40. And cherries, 10, 20, 30, 40. So it seems like whoever made this graph wants bananas to look like they were collected the most and cherries to look like the least because they made the pictures so much bigger and they made the cherries so much smaller. And so even though the same amount of each was collected, the size of the pictures made it look like one was collected more than the other. Right? Pictographs can be easily manipulated by affecting the size and spacing of the pictures. You can group up the pictures together to make it look like it doesn't go as far, right? Doesn't make it look like it goes as long as the other one. But if you evenly space them out and make the size equal, you can see that they're all the same. So where do we see misleading graphs? This video will show you a news report that uses graphs in this way and try to convince you of something that isn't true or isn't as dramatic as it should be. So page 23, question 4, 5, 9, and 11, A, B, C for each of those, and D for 5. Try and complete those. They will talk about how to mislead and create graphs in a misleading way. This, I think, is an important lesson because it teaches you to be a little bit more critical about the things you see. Thank you for listening, and I'll see you next lesson.